Welcome to The Explainer. Today, we're tackling a seriously exciting challenge. We are taking a massive, dense, 6-hour deep dive into cloud-native architecture and distilling the whole shebang into a fast, highly conceptual breakdown of Kubernetes. So if you want to actually understand how modern software scales without getting completely lost in a sea of endless terminal screens, well, you are in exactly the right place. Our source material poses this core question right out of the gate. What is the right way to learn Kubernetes? Okay, let's dive into this, because honestly, the best way to understand this absolute beast of a system isn't to just start staring at code. It's to first grasp the fundamental problem of how we actually deploy applications efficiently today. Here is our roadmap for today's journey. First up, the evolution of computing. Second, inside Kubernetes architecture. Third, the 3 A's of access. Fourth, demystifying pods and probes. And finally, advanced pod patterns. Section 1, the evolution of computing. How did we get here? Before we even touch orchestrators, we've got to anchor our story to the ultimate enterprise goal, and that is simply to deploy the application. The tools have completely transformed, but that core goal, it remains exactly the same. Decades ago, enterprises were racking and stacking physical bare metal servers. It was incredibly slow and, honestly, a massive waste of CPU capacity. Then came the virtualization era, using hypervisors to slice that hardware into virtual machines. Fast forward, and cloud computing abstracted the data center entirely, giving us VMs on demand via APIs. But the real game changer hit in 2013 with Docker and the container era, bringing us these amazingly lightweight, highly portable packages of code. To really grasp why containers just absolutely took over, we have to contrast the architectures. Consider the monolith. It's basically one giant codebase. If just the login feature breaks, the entire app crashes, and rebuilding it takes forever. Now, contrast that with microservices. You're breaking the app down into these small, totally independent pieces. You've got a login service written in Go, a front end in React, maybe an AI inference engine running in Python. They scale easily, and they scale independently. But, and here's the catch, when you suddenly have hundreds of these tiny containerized microservices trying to talk to each other, you absolutely need a way to manage them. Which brings us to Section 2, inside Kubernetes architecture, touring the cluster factory. Think of Kubernetes as the ultimate automated factory manager for your microservices. It's an open source system that actually originated from Google's internal Borg and Omega projects, eventually launching in 2014. Look, if you didn't have this and you were trying to manually manage, say, 200 microservice containers, you'd be stuck writing endless, totally fragile custom scripts just to monitor uptime, heal crash containers, and route your traffic. Kubernetes handles all of that heavy lifting automatically, right out of the box. So let's turn this abstraction into a concrete story. When you issue a command to deploy an app, here is the exact lifecycle it goes through. First, the API server receives your request. Second, the scheduler takes a look at your cluster and assigns your application to a specific worker node. Third, an agent living on that node, called the kubelet, takes the command. And fourth, the container runtime steps in to actually spin up the Linux process. Now, what's really interesting about this is how Kubernetes essentially modularizes the work on that worker node using distinct interfaces. First up is the CRI, or Container Runtime Interface. This clever plugin system allows the kubelet to talk to different tools like Containerd or runc. It's the CRI that's actively responsible for carving out those isolated Linux namespaces and resource-limiting C groups, making sure your container actually runs securely. But those isolated containers need to talk to each other, right? Enter the CNI, the Container Network Interface. The CNI's job is to step in and assign a dedicated IP address to your pod. It works this magic by setting up virtual Ethernet pairs. We usually just call them VETH pairs. It's basically creating a bridge between the isolated pod and the host node's network, allowing for seamless communication across the entire cluster. Finally, we have the CSI, the Container Storage Interface. You see, containers are ephemeral. If they crash, the data inside them just vanishes. So the CSI allows Kubernetes to attach and mount persistent storage volumes directly from cloud providers. It's a brilliant design because the storage drivers live entirely outside the core Kubernetes code. That means your stateful database can easily survive a pod restart without bloating the main system. Pretty cool, right? Moving right along to Section 3, the 3 A's of access. Securing the API server. Remember that API server we mentioned? It's the absolute front door to your cluster, and it acts like an unforgiving security guard. It enforces strict control using the rule of threes. Step 1, authentication. Who are you? It meticulously checks your client certificates or service account tokens. If you pass that, you hit step 2, authorization. Are you actually allowed to do this? It uses role-based access control, or RBAC, to verify if you have permission to, say, delete a deployment. Finally, step 3, admission. Does this action actually meet our cluster's strict policies? Webhooks will validate or even mutate your request, like enforcing resource limits, before it ever gets saved. You absolutely must pass all 3. No exceptions. Section 4, demystifying pods and probes, the smallest deployable unit. Okay, we've talked a lot about the factory managers. Now let's meet the actual workers on the factory floor, the pods. A pod is literally the absolute smallest deployable unit in Kubernetes. But here's the fascinating part. A pod isn't strictly just one container. It actually encapsulates one or more containers. So how do they share an IP address? Well, Kubernetes uses a tiny hidden pause container, and its sole job in life is just to hold the network namespace open. Because of this little trick, containers inside a single pod can talk directly to each other right over localhost. And this brilliant setup is exactly how Kubernetes keeps those apps healthy completely on autopilots. It uses 3 distinct health checks, known as probes. The startup probe checks if a slow-starting app has actually fully booted up. If the liveness probe fails, meaning your app is completely stuck or dead, the kubelet steps in and violently restarts the container to fix it. But if the readiness probe fails, let's say your database connection temporarily dropped, it doesn't kill the app. It just temporarily removes the pod from the network traffic rotation until it recovers, so you get no dead routes and no errors for your users. Section 5, advanced pod patterns, multi-container synergy. Because a single pod can actually hold multiple containers that share that local network and storage, we can build some highly advanced architectural patterns. The first one is the init container pattern. Think of these guys as your dedicated setup specialists. An init container runs its tasks completely sequentially. It might be cloning a GitHub repository or maybe waiting for a database to become fully available. Only after the init container successfully completes its job and then terminates does the main application container finally start up. This keeps your main image incredibly clean and totally bloat-free. Then we have the sidecar pattern. These are auxiliary containers that run right alongside your main application container for its entire lifecycle. They handle all the essential utility tasks, securely proxying traffic, collecting system metrics, or forwarding logs. This has massive relevance in modern service mesh architectures. The sidecars handle all the complex network routing and security encryption, and you don't have to write a single line of that code into your main application. As we bring all of these incredible pieces together, I really want you to consider this quote directly from our source material. Always remember, the main aim is to deploy the application, and we need to deploy the application the best way possible using Kubernetes. That's it. All of this architectural complexity, the API servers, the modular interfaces, these advanced pod patterns, it all serves one beautiful, totally unified purpose: shipping reliable software to your users. Which leaves us with one final provocative thought based on everything we've explored today. With the immense power of orchestrating microservices, robust self-healing probes, and advanced multi-container patterns right at your fingertips, how will you architect your next deployment? Thank you so much for joining me for this explainer. I really hope it brought some incredible clarity to the chaos of Kubernetes.